do that tomorrow yourselves with a tuning fork. So now next, in those videos we saw, they talked a bit about fundamental frequency. So the fundamental frequency is defined as the lowest frequency that can generate a standing wave. Okay? So basically, it's where we see that standing wave making an antinode. So here, this would be fundamental frequency. And so this is like with an air column, and this is like where there's two springs, one string with two people holding it. This one is the fundamental frequency. Okay, and then after that we have different levels of harmonics. So there's all kinds of ways that music really ties into physics. That's what your harmonics are in physics, is where, or in music, is where you have the next frequency that would make a standing wave. So now we go back to our universal wave equation, and we're going to do a bit more math again, okay? So you can take out your data sheets in your calculators. And let's review, what is your universal wave equation? It's only three things. Morgan's telling me.
Oh, I don't know.
Well, look at your data booklet. Under waves. V equals F lambda. You knew there was lambda in it somewhere, didn't you?
Yeah.
Yep. That's what you were getting at. Remember that frequency is measured in hertz, lambda is measured in meters, and speed is measured in meters per second. Okay, so let's look at this question. A closed air column resonates with a fundamental frequency of 225 hertz. What is the length of this air column if the speed of sound is 341 meters per second? So write down what you know.
I'll wait till you're done with the question.
Okay, yeah. Okay, so let's write down what we know. Our F is equal to 225 hertz. V is equal to 341 meters per second. And our lambda, well, we're looking actually for length, not for lambda. So we'll set that to big L is equal to question mark. Now let's draw a diagram of the air column that we're working with so that we know how to set this up. We're going to need it, but I'll tell you how we get it. Okay? You'll find your lambda by using this formula, but we're looking for the length of the tube, not for the wavelength. So it's like you're trying to find out what is the length of this tube. Okay, you're not looking for the wavelength of the actual energy wave. So let's say this is our air column. If this is resonating with a fundamental frequency, so that means just the first one, then our wave needs to look like this, just like I showed you here. That's a fundamental frequency of a closed-end tube. And it's resonating, so that's our antinode, so we hear that resonance. Okay? So now, what did I tell you this was? How many wavelengths? A quarter. So this is a quarter of a wavelength. So this quarter of a wavelength needs to be exactly the length of the actual tube. Because if that's resonating there, that is 1/4 of a wavelength, and that's the length of my column. So if we mapped out what we're going to do mathematically here, we can find V is equal to lambda F. This is our first step. And we will rearrange to solve for our lambda. So wavelength equals V over F. We can plug those values in, 341 meters per second divided by 225 hertz. So 1.515 repeating meters. Remember to include your units as you're going along so that you remember. Now step 2, because we actually want to find the length of the air column, not the wavelength. But we said that the length of the air column is 1/4 of the actual wavelength. So then L is equal to lambda over F. 4 F. Okay? I can take that wavelength and divide it by 4. I'll show you how I did that. So if, well, does that make sense?
Can we just multiply by 1/4 too?
Yep, or multiply by 1/4. If you like to think about it that way just to help you out, that's fine too. So L is equal to 1.515 meters divided by 4. So for sig digs, we have 3, so 0.379 meters. Or you could go 3.79 times 10 to the negative 1 meters.